Please try this problem. Now let's discuss the problem. Here's a summary of the solution for part A, and let's go through the solution step by step. The concepts that are mentioned in the problem indicate that we should apply a Newton's second law problem-solving framework. Now let's identify the question. The question is the minimum force to make the box move up the wall. Clearly, we already know the direction of the upward force, so I'll interpret the question to be asking us for the magnitude. I'll symbolize that with the symbol capital F sub up, written without an arrow on top. Now, as we discussed in the previous video, when the question asks us for the minimum force to make the box move up the wall, we can actually interpret that question as asking us for the borderline upward force, such that the box is on the borderline between sliding up the wall and not sliding up the wall. So let's reinterpret the question as asking us for this borderline upwards force. The problem says that this is the minimum force to make the box move upwards. So, if the force is greater than that minimum, we know that the box will slide up the wall. And if the force is less than that minimum, the box will not slide. That also matches our common sense. It's the upward force that's going to make the block start sliding up the wall. So it makes sense that a larger upward force would tend to make the box slide up the wall, and a smaller upward force would tend to result in the box not sliding up the wall. Now let's make a plan for how we're going to attack part A. In order to determine this borderline upward force, we need to make the assumption that we're at the borderline. We'll assume that the magnitude of the upward force equals the borderline value. Now, if the upward force were greater than the borderline, the box would slide up. And if the force were less than the borderline, the box would not slide. What's going to happen when we're exactly at the borderline? At the borderline, should we say that the box will or will not slide up the wall? Well, as we discussed in the previous video, when the upward force is equal to the borderline value, you can assume either that the box will slide or that the box will not slide, whichever is convenient for solving that part of the problem. Although this might seem strange, we've seen in the previous video that this is a valid problem-solving technique. So which assumption is more convenient? Well, we just need to notice that this is a minimum problem. Because in the previous video, we learned a method for dealing with minimum or maximum problems involving whether an object will slide. Here's that method on the friction handout. And so we've learned that for this type of minimum or maximum problem, the useful, convenient assumption is to assume that at the borderline value, the object does not slide. So we'll follow that strategy and we'll assume that at the borderline, the object will not slide. Write down your assumption. For part A, we're going to assume that at the borderline, the box does not slide. That might seem to conflict with the wording of part A, which refers to the box moving up the wall, but we saw in the previous video that as a problem-solving technique, this is still a valid assumption. While the problem seems to be asking for the minimum force to make the box start moving, what the problem is really asking us for is the borderline force, at which the box is on the borderline between sliding and not sliding up the wall. And at that borderline, we can assume either that the box will or will not slide, as is convenient for that part of the problem. So again, our plan for part A is to assume that at the borderline force, the box does not slide. On this problem, if the box is not sliding, that means that the box is motionless. So I'll make a note that the velocity is 0 to indicate that the box is motionless based on our assumption for part A. Check that the given units are SI units. Yes, kilograms and newtons are SI units. Now let's work on the free body diagram for part A. First, we identify the object's weight. Then we ask what is touching the box. Well, the box is being touched by the wall. The wall is the type of thing that we treat as a surface, so the wall exerts a normal force on the box. The problem indicates that there will also be friction between the wall and the box, so we identify a frictional force, should it be static or kinetic friction for part A. Well, we've decided that for part A, we're going to assume that the box does not slide. When the object is not sliding across the surface, we apply static friction. Also, we're assuming that the force is equal to the borderline value. We're assuming that the object is on the borderline of sliding, which means that the static friction is maxed out. So we're going to apply maximum static friction. The problem tells us directly that there is a horizontal force of 180 newtons being exerted on the box. So we know that we need to include that horizontal force in our free body diagram. We could refer to that as an applied force and use this symbol, but there's also going to be another applied force, so to speak, the upward force. So to distinguish between those, I won't call either of those the applied force. Instead, I'll refer to this force as the horizontal force to distinguish it from the upward applied force. And as I was just saying, the wording for part A tells us that there will also be an upward force exerted on the box. So we also need to include that upward force in our free body diagram. And again, I'm going to use the symbol capital F sub up for this force and capital F sub capital H for this force to try to carefully distinguish between the horizontal applied force and the upward applied force. Read and reread the problem carefully to make sure you're getting all the necessary information. Did you realize that on this problem there were two separate applied forces, a horizontal force and an upward force? The horizontal force was shown in the sketch that we were given. The upward force was not explicitly shown in this sketch, but we know that it exists from the wording of part A. We don't know specifically who is touching the box in order to exert the horizontal force or the upward force, but of course we know that they exist from the wording of the problem. There doesn't appear to be anything else that is touching the box, so there are no other forces that we need to include in the free body diagram. We use these rules to determine the directions of some of the forces. For example, the direction of the normal force exerted by the surface of the wall on the box should be perpendicular to and away from the surface of the wall. So that's this direction to the left. To the left is the direction that is perpendicular to and away from the surface of the wall. We use this rule to find the direction of the maximum static friction force. Ask yourself, in what direction are we imagining the object to be on the verge of sliding? Well, we're imagining that the object is on the borderline of sliding up the wall, on the borderline of sliding up the wall. So the maximum static friction has to be parallel to the wall and down the wall. The maximum static friction will be parallel to the wall pointing down, because the object is on the verge of sliding up, so to prevent that, the maximum static friction has to point down. Remember that the normal force is always perpendicular to the surface, and the frictional force is always parallel to the surface. In this case, the wall is a vertical surface, so the normal force is horizontal, and the frictional force is vertical. The direction of the horizontal force was given in the problem. It was referred to as a horizontal force of 180 newtons, and then in the sketch that we were provided, we can see that horizontal 180 newton force points to the right. So here we show the horizontal force pointing to the right. And part A refers to another force that's being exerted upward. Well, clearly the direction of that upward force is upward. I believe that this is the first problem that we've seen in this video series where there were 5 forces on the object. So take your time and make sure that you correctly identify all the forces on the object for your free body diagram. Now we work on the force table. We are given a value for the magnitude of the horizontal force, 180 newtons. So we write that value in the first row of our force table. We have special formulas for the magnitudes of the weight and the maximum static friction. So we use those special formulas to determine or represent those magnitudes. Remember, we're applying static friction for part A because for part A, we're assuming that the box does not slide at the borderline. Remember that we're assuming that the object is on the borderline of sliding. That's how we know that static friction is at its maximum. And that's the reason that we can use this special formula. We can only use this special formula for maximum static friction when we are assuming that static friction is at its maximum. But that is the most typical situation that you would most typically see for static friction problems. Because we are applying static friction for part A, we should be careful to use 0.4 for our coefficient of friction rather than 0.3. We have no given value for the normal force or the upward force. After all, the upward force is what the question is asking us about. There's no special formulas for those two forces, so we represent the unknown magnitudes for the normal force and the upward force with symbols. For example, we use the symbol capital F sub up, written without an arrow on top, to stand for the magnitude of the upward force. Notice that the horizontal force and the upward force are treated differently in the first row because we know the value for the horizontal force and we don't know the value for the upward force. Now we have to choose our axes. We usually prefer to choose an axis that points in the object's direction of motion. Now for part A, we're actually assuming that the box is not moving, but in part A, the box is on the borderline of moving up. And furthermore, in part B, the box really will be moving up. So let's choose a positive y-axis that points up, and I'll choose an x-axis that points to the right. All 5 of our forces are either parallel or anti-parallel to the x or the y-axis. So we can use this simple rule to break all 5 of the forces into components. We won't need to use SOHCAHTOA for any of our 5 forces for this problem. Include plus signs in front of the positive components because that will help you to remember the crucial negative signs in front of the negative components. Now let's work with the Newton's second law equations. For part A, we're assuming that the box does not slide, which means for this problem that the box is motionless. This box is completely motionless in part A for both components. So we can substitute 0 for both a sub x and a sub y for part A. This is the reason that it was convenient to assume that the box does not slide for part A. It's convenient to assume that the box does not slide for part A because that allows us to substitute 0 not only for a sub x, but also for a sub y. Now, originally there are 2 unknowns in the Newton's second law y equation, and only 1 unknown in the Newton's second law x equation. So we begin by solving the Newton's second law x equation for n. We do that by adding n to both sides. The advantage of this approach is that it doesn't only get n by itself, but it also at the same time gets rid of the negative sign in front of the n. Now we take the result that we determined for n and substitute it into the Newton's second law y equation. And at this point, the Newton's second law y equation has only 1 unknown, so we can solve this equation now for f sub up. Our result is that f sub up is 121 newtons. Now we can use our result to answer the question for part A. When we were solving part A, we interpreted f sub up as the borderline force at which the object is on the borderline between sliding up the wall and not sliding. But now that we're writing down our answer to part A, I'll go back to the wording that was used in the problem. The problem referred to it as the minimum force to make the box start moving, and I'll use that wording when I'm phrasing my answer to the question for part A. Check to make sure you've answered the right question and that you've answered all parts of the question. For example, we need to notice that we're still going to have to answer part B. check to make sure you include units on your answer. Do our results make sense? This symbol stands for a magnitude, so it makes sense that it came out to be positive. 180 newtons is the magnitude of the horizontal force. Well, the horizontal force is trying to begin the box moving to the right through the surface of the wall. To prevent that from happening, the normal force is going to have to cancel the horizontal force. So yes, it does make sense that we determined that the magnitude of the normal force equals the magnitude of the horizontal force. This symbol stands for another magnitude, so it makes sense that this result is positive. Does the size, 121 newtons, of this result make sense? Well, we know that the magnitude of the weight force is 49 newtons, and in the course of our work on the Newton's second law Y equation, we also determined the magnitude of the maximum static friction. At this point, we determined that the magnitude of the maximum static friction is 72 newtons. So I'll record that here. Now, this upward force is trying to begin the box moving upwards. But remember that for part A, we're assuming that the box will not slide. So to preserve that assumption and make sure that the box does not slide despite this upward force, we need the cooperation between the weight force and the maximum static friction to cancel the upward force. Well, 49 newtons plus 72 newtons equals 121 newtons. So all of these magnitudes came out to be exactly what they had to be in order for the cooperation between the weight force and the maximum static friction to cancel the upward force and preserve our assumption that the box will not begin sliding in part A. So yes, the size of this result does make sense, and I tried to draw the length of this arrow equal to the sum of the lengths of this arrow and this arrow to indicate that relationship. Here again is a summary of our solution for part A. Part A was a minimum problem dealing with whether the box would slide, and we know a method for dealing with that type of problem. The method is to assume that we're at the borderline and to assume that at the borderline the box does not slide. Those assumptions mean that we should be using maximum static friction for part A, and that allows us to use the special formula for maximum static friction. And the assumption that the box is not sliding also justifies us in substituting 0 for both a sub x and a sub y. Now let's look at the solution for part B. Here's a summary of the solution for part B. Let's go through the steps. Part B asks for the acceleration, and I'll interpret that as asking for the magnitude and direction of the acceleration. Part B says this force is continually applied. Which force do they mean? They mean the minimum force that we just got finished determining in part A. Remember, the force that we just finished determining in part A was 121 newtons for the upward force magnitude. So when part B says that this force is continually applied, what they mean is that we should use our value of 121 newtons for the magnitude of the upward force, which we determined in part A, and we should continue to use that value for the magnitude of the upward force in part B. So I'll make a note of that here. Of course, that means that we're going to continue to assume that the upward force is at the borderline value, at which the object is on the borderline between sliding up the wall and not sliding. Now, at the borderline value, we can assume either that the box will slide or that the box will not slide, whichever is convenient for solving this particular part of the problem. So what's the convenient assumption for part B? Well, for part B, we have to determine the box's acceleration once the box actually starts moving. The only way to determine the box's acceleration once it starts moving is to assume that the box is moving, to assume that the box is sliding up the wall. After all, if we assumed that the box was not moving, then the acceleration would be 0, and clearly that's not what they're going for in part B. So for part B, we have to assume that at the borderline value, the box does slide up the wall. For part B, let's write down our new assumption that the box will slide at the borderline value. This is the opposite of the assumption that we made for part A, but that's okay. It turns out that it's a valid problem-solving technique to change your assumption about what happens at the borderline value for different parts of the problem. We already demonstrated that approach in the previous video, and it looks like we're going to use a similar approach now for part B of this video. Write down your assumptions. We're assuming that the magnitude of the upward force is equal to 121 newtons, the borderline value, and we're assuming that the box will slide up the wall at the borderline. For this problem, if the box is sliding up the wall, that means that the box will be moving upwards. So we'll draw an upward velocity vector to indicate the object's direction of motion based on our assumptions for part B. Which parts of our free body diagram from part A can we continue to use for part B? And which parts of the free body diagram do we need to change for part B? Well, we need to change how we're dealing with friction. For part B, we're assuming that the box is sliding. When an object is sliding along a surface, we apply kinetic friction, not static friction. In part B, we're assuming that the box is sliding up the wall. So for part B, the kinetic friction to oppose that should point parallel to and down the wall. There's no reason to make any other changes for any of the other forces in the free body diagram for part B. Which parts of our force table from part A do we need to change for part B? Well, we need to change the part of the force table that deals with friction. Now in the force table, we should be dealing with kinetic friction, not static friction. So for part B, we need to use the special formula for the magnitude of kinetic friction. Since we're now dealing with kinetic friction, we should be using the number 0.3 as our coefficient of friction. We should no longer be using the number 0.4. For part A, we didn't know what the magnitude of the upward force would be. But now, in part B, we do know this magnitude. Remember, we're making the assumption now in part B that the magnitude of the upward force is 121 newtons. So that's another way that we can change our force table from part A to part B. For part B, we can say that the magnitude of the upward force is 121 newtons. That's based on this information. The problem told us, for part B, this force is continually applied. And what they're referring to there is the minimum force that we determined in part A. In part A, we determined the magnitude of that minimum force as 121 newtons, and we should continue to apply that magnitude for part B. The problem does not say that the magnitude of the normal force will be the same for part B as for part A, so to be on the safe side, I'm not going to assume that the normal force for part B will have the same magnitude that we determined for part A. I'll just use a symbol for the magnitude of the normal force, and we'll let the Newton's second law equations figure out for us whether the normal force is the same or different in part B compared to part A. The box has the same mass in part B as in part A, so there's no reason to make any change for our entries for the weight force. Now we work with the Newton's second law equations for part B. In part B, we assume that the box does slide up the wall, which means that the box is moving upwards. The box will be motionless horizontally in the x component. Since the box is motionless in the x component, we can still substitute 0 for a sub x. Since the box is moving in the y component vertically, there's no reason to substitute 0 for a sub y, and in fact remember that a sub y is what we're going to have to figure out in order to be able to answer the question for part B. We begin by solving the Newton's second law x equation for the magnitude of the normal force, and it turns out that the normal force does have the same magnitude in part B as it had in part A, 180 newtons. Then we substitute that into the Newton's second law y equation, and we can then determine that a sub y is positive 3.6 meters per second squared. Now we can answer the question for part B. Because a sub x is 0, the overall acceleration should have the same magnitude and direction as a sub y. A sub y is positive. Our positive y direction is up. So the direction of the acceleration is up, and the overall acceleration will have the same magnitude as a sub y, 3.6 meters per second squared. Check that you've answered the right question and that you've answered all parts of the question. We now have finished answering all parts of the question. Check to make sure that you included units in your answer. Check if your results make sense. Does it make sense that the magnitude of the normal force is the same for part B as for part A? Well, we know that the normal force has to cancel the horizontal force to prevent the box from being pushed into the surface of the wall. The horizontal force is the same in part B as in part A, so yes, it does make sense that the normal force is the same in part B as in part A. Does it make sense that our result for a sub y is positive? The positive y direction is up, so we can say that the acceleration vector is pointing up. Does that make sense? Well, yes. In part B, the box is beginning at rest and then beginning to move up the wall. In order for the box to begin at rest and then begin moving upwards, the acceleration must point upwards. So yes, it does make sense that we determined that the acceleration is upward pointing for part B. And the magnitude 3.6 meters per second squared is inside of this typical range. So in that sense, the magnitude of this result seems reasonable. Here again is a summary of our solution for part B. Part B told us that this force, which we determined in part A, continues to be applied in part B. So we knew that in part B we should use the 121 newtons value that we determined in part A, and for part B, in the first row of our force table, we can now say that the magnitude of the upward force is 121 newtons. 121 newtons represents the borderline value of the applied force. At the borderline, we can assume either that the box does or does not slide, whichever is convenient for this part of the problem. Part B is asking for the box's acceleration once the box begins moving up the wall, and the only way to figure out the box's acceleration once it's actually moving is to assume that the box is sliding and moving up the wall. So for part B, we make the assumption that the box does slide up the wall at the borderline value for the upward force. That meant that we had to change from maximum static friction to kinetic friction. And assuming that the box is now sliding up the wall meant that we can still substitute 0 for a sub x, but we no longer substitute 0 for a sub y. I believe that this is only the second problem in this video series which involves a vertical surface, the wall, rather than a horizontal surface or an inclined plane. So make sure that you understand how we determined the directions of the normal force and the friction force for this vertical surface, and why a sub x is 0 when the object is moving parallel to the vertical surface. Here's a comparison of the key assumptions that we made for our solution of part A and for our solution of part B of the problem. In part A of the problem, we assumed that the box does not slide at the borderline value. In part B of the problem, we assumed that the box does slide at the borderline value. It's a valid problem-solving technique to shift between those two assumptions as is convenient for different parts of the problem. And here's a side-by-side comparison of some of the key steps in our solution for part A and some of the key steps in our solution for part B. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.